So have you ever stopped to wonder how developers actually build the massive, complex software we use every single day? Well, the secret, a lot of the time, is this powerful idea called object-oriented programming, or OOP for short. And in the next few minutes, we're going to break down its blueprints.
To really get why OOP was such a game changer, we kind of have to travel back in time. As this quote points out, the software world was staring down a serious crisis. Projects were just getting bigger and more complicated, and the old ways of writing code, they just weren't cutting it anymore.
I mean, just imagine trying to find and fix one tiny mistake in a book that's millions of pages long, written by a whole bunch of different people. It's a nightmare, right? That's exactly the kind of mess developers were dealing with. The sheer complexity was just overwhelming.
And yeah, this whole mess actually has a name: the software complexity crisis. It was a clear signal that something fundamental had to change in how we thought about building software.
The solution, at its core, was actually beautifully simple. Instead of just writing these long, tangled lists of instructions, the big question became, what if we organized our code the same way we see the world around us, as a collection of distinct, self-contained things, or objects?
And that right there brings us to the very heart of object-oriented programming. It's a whole new way of thinking, really, built on just a few key ideas that completely revolutionize software design. So, let's break them down.
First up, you've got the class. The best way to think about a class is as a blueprint. So if you were going to build a car, the class is that detailed design plan. It says, okay, every car is going to have wheels, an engine, and it needs to be able to start and stop.
An object, then, is the actual thing you build from that blueprint. It's not just some abstract idea of a car, it's your specific red BMW sitting in the driveway. It's a real, living instance that was stamped out from that car class, with its own unique details.
Now, here's where it gets really clever. We can build on these blueprints using something called inheritance. This lets us create a new, more specific blueprint that just reuses everything from a more general one. You know, a truck is a kind of vehicle, right? So it inherits all the basic vehicle stuff, but then it can add its own unique features, like a giant cargo bed. It's all about not reinventing the wheel, literally.
And finally, we have polymorphism. Now stick with me because this word sounds super complicated, but the idea behind it is incredibly powerful. Imagine you've got a garage with a car, a truck, and a motorcycle. You can just treat them all as a vehicle and tell them all to start. Polymorphism is the magic that lets each one respond in its own way. The car's engine purrs, the truck's diesel engine rumbles to life, and the motorcycle kicks on its starter. Same command, different results. That's how you build flexible, adaptable code.
Okay, so we've got the big ideas down. But in the real world, developers need tools to actually define these blueprints. And that choice often boils down to two key tools: interfaces and abstract classes.
Let's put them side by side. On the one hand, an interface is like a strict contract. It just says, hey, any object that signs this contract must be able to do these things. It doesn't care how you do them. On the other hand, an abstract class is more like a partial blueprint. It can give you some of the basic wiring already done, some shared code, but then it leaves other specific parts for you to finish yourself. So really, it all boils down to this trade-off. If you need maximum flexibility to make a whole bunch of different, unrelated things follow the same rules, you go with an interface. But if you're building a family of closely related things that share a lot of the same DNA, an abstract class is your best bet for sharing code and keeping things organized.
Now, as developers started building things this way, they started to notice something. They were solving the same types of problems over and over and over again. And that led to this brilliant idea of design patterns, which are basically just proven, reusable solutions to common challenges.
And this book right here, this is basically the Bible on the subject. A group of 4 authors, famously known as the Gang of 4, wrote it. They identified 23 of these core patterns, giving developers a shared vocabulary and a toolkit of elegant, battle-tested solutions.
To really see why this is so cool, let's look at a real-world problem. Imagine you're building an app with a window, and you want to give the user options to add, say, a border or a scroll bar, or maybe both in any combination they want. Now, if you tried to solve this the old-fashioned way with just inheritance, you'd have to create a separate class for every single possibility. A window with a border, a window with a scroll bar, a window with a border and a scroll bar. It gets out of control fast. You'd end up with 15 different classes. This is what's known as a class explosion, and trust me, it's a maintenance nightmare.
But check this out. The Decorator pattern offers a much smarter way. Instead of creating tons of new classes, you just take your original window object and you wrap it with new functionality. Want a border? Wrap it in a border decorator. Want a scroll bar too? Just wrap it again. You can stack them on the fly, giving you endless combinations without that class explosion. It's so much more flexible.
So we have our core concepts, our tools, and our patterns. But what guides a developer to make good design choices in the first place? Well, that's where the solid principles come in. You can think of them as the philosophy behind great OOP design.
Solid is just an easy way to remember 5 key principles that really act as a developer's North Star. S means every class should have only one job. O means your code should be open to adding new stuff, but closed to being changed. Think of it like adding new Legos without having to break the ones you already built. L is a fancy one, but it just means child classes should work perfectly in place of their parents. I means don't force a class to have functions it doesn't need. Keep contracts small. And finally, D means your big picture code shouldn't get bogged down in tiny details. It helps keep everything neat and tidy.
So why bother with all these rules? Well, it's all about quality. Following Solid helps you write cleaner code, dodge common mistakes, sometimes called code smells, and most importantly, build software that doesn't fall apart the second you try to add a new feature. It's about building things to last.
All right, let's wrap this up with the key takeaways. OOP is all about tackling complexity by modeling the real world. Interfaces and abstract classes are your go-to tools for defining those models. Design patterns are your cheat sheet of proven solutions. And the solid principles? They're your guide to making sure what you build is high quality and built to last.
In the end, object-oriented programming isn't just a list of technical rules you have to follow. It's really a mindset. It's a way of thinking about solving problems that champions clarity, flexibility, and reuse. So the real question isn't just what these concepts are, but how are you going to use them to build better software?